the name of Almighty God, I'm Asas Hankoshan. Today I want to talk about the theory for the transfer of diluted species interface. The transfer of diluted species interface provides a predefined modeling environment for studying the evolution of chemical species transported by diffusion and convection as well as migration due to electric field. The physics interface assumes that all species present are dilute, that is, the air concentration is also compared to a solvent, fluid, or solid. As a rule of thumb, a mixture containing several species can be considered dilute when the concentration of the solvent is more than 90% of molar. Due to the dilution, mixture properties such as density and viscosity can be assumed to correspond to those of the solvent. When studying mixtures that are not dilute, the mixture and transfer properties depend on the composition, and a different physics interface is recommended. See the transfer of concentrated species interface in the for more information. Fixed law governs the diffusion of the solutes, dilute mixtures or solutions, while a phenomenon of ionic migration is sometimes referred to as an electrokinetic flow. The transfer of diluted species interface supports simulations of chemical species transfer by convection, migration, and diffusion in one dimension, two dimension, three dimensions, as well as for asymmetric components in one dimension and two dimensions. In this section, we want to go through the adding transfer through migration, material balance formulation, cross-finally fusion, Dankworth's flow boundary condition, equilibrium reaction theory, mass balance equation, mass sources for species transfer, solving a diffusion equation only, supporting electrolytes, the packed with feature references. Note that some features explained in this section require certain add-on modules. For details, you can see computer.com/product/specifications. This section also includes the theory for the transfer of diluted species in porous media interface, absorption, convection in porous media, diffusion in porous media, dispersion, mass balance equation for transfer of diluted species in porous media, mass transfer in fractures and reactions. Now I want to go through the mass balance equation. The default null attribute to the transfer of diluted species interface models chemical species transfer through diffusion and convection and solves the mass conservation equation for one or more chemical species I when they have the derivative of Ci based on the time plus delta Gi plus U delta Ci is equal to Ri. Equation 3-13 its form above includes the transfer mechanisms diffusion and convection. If migration electric field is activated, only available in some add-on products, the migration mechanism will be added to the equation as well. See more details in the section adding transfer through migration. Ci is the concentration of species based on the unit molar per cubic meter. Di denotes the diffusion coefficient based on the unit square meter per second. Ri is the reaction rate expression for the species based on the unit molar per cubic meter second. U is the mass average velocity vector based on the unit meter per second. Gi is the mass flux diffusive flux vector based on the unit molar per square meter second. The mass flux relative to the mass average velocity Gi based on the unit is molar per square meter second is associated with the mass balance equation above and used in the boundary conditions and flux computations. The transfer of diluted species interface always includes mass transfer due to the molecular division. In this case, the mass flux Gi defines the diffusive flux vector. Gi is equal to minus d delta Ci, and input field for the diffusion coefficient is available. When migration electric field is activated, the migration term is also added to the diffusive flux vector as shown in this section, adding transfer through migration. The third term on the left side of equation 3-30 describes the convective transfer due to the velocity field u. This field can be expressed analytically or obtained from coupling the physics interface to one that solves for fluid flows such as laminar flow. Notes that all fluid-fluid interfaces solve for the mass average velocity. On the right-hand side of the mass balance equation 3-30, RI represents a source or sink term, typically due to a chemical reaction or desorption on a porous matrix. To specify RI, another node must be added to the transfer of diluted species interface. The reaction node, for example, which includes an input field for specifying reaction expression using the variable names of all participating species. Now I want to go through the equilibrium reaction theory. The feature equilibrium reaction is described in this section. A chemical equilibrium reaction system is defined by the stoichiometry of the reaction and relation between the chemical reactivities of the chemical species participating in the reaction, the equilibrium react condition. The kinetics of the reaction is so fast that the equilibrium condition is fulfilled at all times in all space coordinates. The equilibrium condition is commonly based on the stoichiometric coefficients VI dimensionless of the reaction, the species activities of the reacting species I are dimensionless, and the equilibrium constant equilibrium 1 according to equilibrium is equal to the multiplication. The lower boundary I belongs to products I to the power of VI divided by multiplication of the lower boundary I belongs to reactants I to the power of minus VI, where the species activities are defined as I is equal to gamma Ci and Ci divided by Ci0, where Ci0 based on the SN is molar per cubic meter is the standard molarity, and gamma is Ci dimensionless and activity coefficient. Defining the stoichiometric coefficients, positive for products and negative for reactants. The above equilibrium condition can also be written as equilibrium is equal to multiplication. Lower boundary is I to the power of VI. The equilibrium reaction node solves for reaction rate so that the equilibrium condition is always fulfilled in the domain. It is available for the chemical reaction engineering module, battery design module, corrosion module, electrochemistry module, electrodeposition module, and the fuel cell and electrolyzer module. Gamma Ci is set to unity when the equilibrium constant is selected in the settings window for non-unity activity coefficients. User-defined equilibrium conditions can be used. Now I want to go through the equilibrium reactions and inflow boundary conditions. Contradictory constraints arise if the boundary conditions for concentrations or activities are set to that so that the domain equilibrium condition is not fulfilled. A special treatment is therefore needed at inflow boundaries where the concentrations are set for all species in the mass transport interfaces. One way of avoiding competing constraints on an inflow boundary is to add an additional reaction coordinate degree of freedom. Solve for to create a set of modified inflow concentrations that fulfill the domain equilibrium condition. The reaction coordinate gives rise to a concentration shift, which is the offset to the inflow concentration provided by the user. The shift for each species obeys the stoichiometry of the reaction and equilibrium expression. The modifying flow concentrations are then used in the boundary conditions for the domain mass transport equations. The resulting modifying flow concentrations can be seen as a essential solution for a batch reactor with the usual flow concentrations as initial concentrations. In addition, the domain reaction rate degree of freedom of the equilibrium reaction is constrained to zero on all inflow boundaries. Now I want to go through the equilibrium reactions and concentration boundary conditions. No special treatment is made with regards to input concentration values of the concentration boundary node. Using this feature, you can explicitly set one or a set of concentrations. The equilibrium condition acts on the rest of the concentrations. However, there is no solution to the problem if more concentrations than the number of species minus the number of equilibrium reactions are set using this feature. Now I want to go through the equilibrium reactions and time-dependent simulations. Spurious oscillations may occur in a time-dependent problem if the initial conditions don't fulfill the equilibrium conditions. Since equilibrium reactions are assumed to be infinitely fast, the solution is initialize the problem using an additional study step. Solving for a stationary problem with all non-equilibrium reactions rates set to zero. Manual scaling of the reaction rate dependent variables is needed in this study step. Now I want to go through the material balance formulation. The default node attributed to the transport of diluted species interface assumes the chemical species transport through diffusion and convection depending on the module's license. A checkbox to activate migration is available and implements the mass balance equation in equation 3-30. Two formulations of the mass balance are available. These are referred to as the non-conservative and conservative form. Non-conservative conservative form is the derivative of concentration based on the time plus delta GI plus U delta C is equal to R based on the equation 3-32. And the conservative formulation is derivative of concentration based on the time plus delta GI plus delta CU is equal to R based on the equation 3-33. In these equations, Ji is the diffusive flux vector, U is the solvent velocity field, and R is the production or consumption rate expression. The non-conservative is often more numerically robust and therefore chosen by default for the interface. This formulation, however, disregards density change in the fluid. This can be seen by expanding the conservative convection term using the chain rule. One of the resulting terms C delta U equals 0 for an incompressible fluid, which results in the non-conservative form. To switch between the two formulations, click the Show button and select Advanced Physics options. Now I want to go through the solving a diffusion equation only. Remove the convection term from the equation 3-32 and equation 3-33 by clearing the convection checkbox in the transport mechanism section for the transfer of diluted species to interface. The equation has the equation then becomes such as the derivative of the concentration based on the time is equal to delta Ji plus R. Now I want to go to the mass source for species transport. Note that the features below are only available in the limited set of add-on products. For a detailed overview of which features are available in each product, visit comsu.com/product/specifications. There are two types of mass sources in transport of diluted species interface: point sources and line sources. Now I want to go through the point sources. The point source is theoretically formed by assuming a mass ejection QC based on the size in molar per cubic meter a second in a small volume delta V, and then letting the size of the volume tend to zero while keeping the total mass flux constant, giving a point source strange Q prime PC based on the size in molar per second. This can be expressed as the limit delta V to go to the zero integral the lower boundary is delta V QC is equal to QAPC based on the equation 3-34. An alternative way to form a point source is to assume that mass is extracted through the surface of a small object. Letting the object surface area tend to zero while keeping the mass flux constant results in the same point source. For this alternative approach, effects resulting from the physics object's volume need to be neglected. The weak contribution we have a QBC TSC is added at point in the geometry, as can be seen from equation 3-34. QC must tend to plus or minus infinity as delta V tends to zero. This means that in the theory, the concentration also tends to plus or minus infinity. Observe that point refers to the physical representation of the source. The point source can therefore only be added to a points in 3 dimensional components and to points on the symmetry axis in the 2 dimensional axis symmetry components. Other geometrical points in 2 dimensional components represents physical lines. The finite element representation of equation 3-34 corresponds to a finite concentration at a point with the effect of the point source spread out over a region around the point. The size of the region depends on the mesh and on the strength of the source. A finer mesh gives a smaller affected region, but also a more extreme concentration value. It is important not to mesh too finely around the point source, since that is can result in unphysical concentration values. It can also have a negative effect on the condition number for the equation system. Now I want to go through the line source. A line source can theoretically be formed by assuming a source of strange QLC between is molar per cubic meter second located between a tube with across section delta S, and then letting delta S tend to zero while keeping the total mass flux per unit length constant. Given a line source strange QLC based on the unit is molar per meter second. This can be expressed as limit delta S tends to zero and the integral the lower boundary is delta S QLSC is equal to QLSC as in the point source case. An alternative approach is to assume that mass is injected, extracted through the surface of a small object. This results in the same mass source but requires that effects resulting from the physical object's volume are neglected. The weak contribution QLSC test C is added on lines into the dimension or at points in two dimension, which represents cut-through views of lines. Line sources can also be added on the axisymmetry line in two-dimensional axisymmetry components. It cannot, however, be added on geometrical lines in two dimensions since those represent physical planes. As with a point source, it is important not to measure too finely around the line source. For feature node information, see line mass source and point mass source. For the reacting fluid in a porous media diluted species interface, which is available with the CFD module, chemical reaction engineering module, or battery design module, these shared physics nodes are renamed as follow. The line mass source node is available as two nodes, one for the fluid line source and one for the species line source. The point mass source node is available as two nodes, one for the fluid point source and one for the species point source. Adding transport through migration. Note that migration is only available in a limited set of add-on products. For detailed overview of which features are available in each product, visit computer.com/product/specification. In addition to transport due to convection and diffusion, to transfer of diluted species interface supports ionic species transport by migration. This is done by selecting the migration electric field checkbox under the transport mechanism section for the physics interface. The mass balance then becomes the derivative Ci based on the time plus delta multiplied by minus di delta Ci minus Zi UMI for the constant Ci delta V plus Ciu is equal to Ri based on the equation 3-36, where Ci based on the SI is molar per cubic meter denotes the concentration of a species I, Di based on the SI is square meter per second is the diffusion coefficient of a species I, U based on the SI is meter per second is the fluid velocity, F based on the SI is ampere second per molar refers to a Faraday's constant. V is based on the SI unit is volts, denotes the electric potential. Zi is dimensionless, is the charge number of the ionic species, and UMI based on the SI unit is molar second per kilogram is its ionic mobility. In this case, the diffusive flux vector is as follows: Ji is equal to minus Di delta Ci minus Zi UMI for the constant Ci delta V. The velocity U can be a computed fluid velocity field from the fluid-fluid interface or specify the function of the spatial variables x, y, and z. The potential can be provided by an expression or by coupling the system of equations to a current balance, such as the electrostatic interface component, which is assumed to be a supporting electrolytic present, which simplifies the transport equations. In the case the model charge of species concentration is very low compared to other ions dissolved in the solution. Thus, the species concentration doesn't influence the solution's conductivity and the net charge within the fluid. The Nernst-Einstein relation can in many cases be used for relating the species mobility to the species diffusivity according to the UMI is equal to Di divided by RT, where R based on the SI is joule per molar Kelvin is the molar gas constant and T based on the SI is Kelvin is the temperature. Note that the Nernst-Planck equations interface the ionic species contribute to the charge transfer in the solution. It includes an electron neutrality condition and also computes the electric potential field on the electrolyte. For more information, see theory for the Nernst-Planck equations interface. This interface is included in the chemical reaction engineering module. Thank you so much for watching my tutorial video until the end. Today is 18th of May 2026. Time is 12:31 p.m. Also, you can download the proper and appropriate and related concept multiphysics simulation file from github.com/maxoscript.